Hello everyone, welcome back to Nated Engineering. Today we are doing an exercise on air compressors, power machines and SIGs. The exercise that we are doing is an exercise that I've taken from my textbook and it reads as follows. A three-stage single-acting reciprocating air compressor has a low pressure cylinder of 450 millimeters and a stroke of 300 millimeters. Clearance volume of the low pressure cylinder is 5% of the swept volume. Intake conditions are 100 kilopascal and 18 degrees Celsius. The final delivery pressure is 1500 kilopascal. Intermediate pressures are ideal and intercooling is perfect. Compression and expansion index are 1.3. And then the questions they say. Number 1. Calculate the intermediate pressures. Number 2. Calculate the effective swept volume of low pressure cylinder. Number 3. Calculate the temperature and volume of air delivered per stroke at 1500 kilopascal. Number 4. Calculate the work done per kg of air. And then we're given R as 0.29 kilojoules per kg Kelvin. And this is the information that we are given. We are dealing with a three-stage air compressor. It's single acting and the index of polytropic we are given as 1.3. It's the X represent the number of cylinders that we have in the compressor, which is 3. We are given the diameter and stroke length of the low pressure cylinder as 450, the diameter, and 300 millimeters, which is the stroke length. The initial conditions, pressure and temperature. The pressure is 100 kilopascal and the temperature is 291 Kelvin. Pressure number 4 were given as 1500 kilopascal. This is the PV diagram of the air compressor that we are dealing with. And then we go to question number 1. Question number 1, they say, calculate the intermediate pressures. Intermediate pressures, they are referring to pressure number 2 and pressure number 3. Number 3. We are given pressure number 1 and pressure number 4. This one we have as 100. This one we have as 1500 kilopascal. We are looking for these two. The first thing that we have to calculate for us to be able to calculate these pressures is the stage ratio. Stage ratio, we know it is represented by K, given by the formula, the X root of P X plus 1 divided by P1, where our X is equals to the number of cylinders. How many cylinders are we dealing with? We are dealing with 3 cylinders. It's a 3-stage. Therefore, our X will be 3, which will give us a cube root divided by Px. Our X is 3 plus 1. This tells us that we are going to put P4 here, since we know that 3 plus 1 is 4, divided by P1. The cube root, what is the value of P4? It's 1500. What is the value of P1? It's 100. And this will give us 2.466. And then from here, we know that the stage ratio will be equals to P4 divided by P3 will be equals to K, and also P2 divided by P1 will be K. Also, P3 divided by P2 will be equals to K. We are going to use these two. First, we'll use this one. We're going to use these two. P2 divided by P1, it's equals to K. We have P1, we make P2 the subject of the formula. We're going to get P2 as being equals to P1 times K. Our P1 is 100 and our K is 2.466, where we are going to have our P2 being equals to 246.6 kilo Pascal. And then we move to this one where we are going to calculate for P3. Our P3, we make P3 the subject of the formula. From here, we are going to have P3 being equals to P4 divided by the constant, the stage ratio. We can use this one to calculate for P3, but since P2 we just calculated, I will suggest that we stick to given information for as long as we can. Here, this will be 1,500. It's given information divided by the stage ratio, which is 2.466. And this will give us 608.273 kilo Pascal. And then we go to question number 2. They say, calculate the effective swept volume of the low pressure cylinder. The effective volume, we know it's given by V1, it's this, and it's given by V1 minus V8. Effective volume, it's V1 minus V8. We do not know the value of V1. We also don't know the value of V8. So now our job is to calculate for the value of V1 and V8. What information are we given concerning the pressures? We are told that the clearance volume, this is the condition that they gave us. I didn't write it here, but they told us that the clearance volume, it's equals to 5% of the swept volume. So we're going to say the clearance volume is equals to 0.05 of the swept volume. This is information that we are given. We are also given the diameter and the stroke length of the low pressure cylinder. We know that the pressure that is associated with the diameter and the stroke length is the swept volume. We are going to use those two to calculate for the swept volume. Swept volume is given by area times stroke length. What is our diameter? It's 0.45. What is our stroke length? Is 0.3. Let's square here. And then we're going to get our swept volume as 0.0477 meter cubed. Since we now have the swept volume, let's take the swept volume and put it here. This will be 0.05 times the swept volume, which is 0.0477, and this will give us 0.00239 cubic meters. This is the clearance volume. We are dealing with the low pressure cylinder. The clearance volume is from here to here, which will be V7. Our clearance volume, it's equals to V7. Remember what we are trying to have, it's V8 and V1. Can we use this, the information that we have now, to get V1 or V8? Yes, we can use the V7 to calculate for V8. Since we have pressure number 1 and pressure number 2, we have now V8. We can use V8 to calculate for V. We can use V7 to calculate for V8 using the formula PV raised to N. This will be 7. It's equals to PV. This will be 8 raised to n. Pressure number 7, it's equals to pressure number 2. And our pressure number 2, we calculated and got that it is 246.6 kilopascal. But first, let's make this the subject of the formula, since that is what we are trying to calculate for. V8, it's equals to V7 times P7 divided by P8 raised to 1 divided by the index. V7, we have 0.00239 times this P7, it's equals to P2, which is 246.6, and then P8, it's equals to P1, which is equals to 100 raised to 1 divided by the index, which is 1.3. And then from here, we're going to get our value for V8 as equals to 0.00479 cubic meters. Now we have our V8. We now want to calculate for our V1. We already got V8, we want to get V1. What is it that we know about the swept volume? We know that the swept volume is from here to here, which will be V1 minus V7. V1 minus V7. We are looking for a pressure that its equation include pressure number 1, and we got that this is the pressure that we have its value and its equation include pressure number 1. Therefore, we're going to make V1 the subject of the formula, which will give us Vs plus V7. And then our Vs, which is the swept volume, we have calculated and got our answer as 0.0477 plus V7. Our V7 is here. That's the clearance volume, 0.00239, which will give us 0.0501 cubic meters. Then from there, we come back to what we want to calculate, V1 minus V8, which is the effective volume. V1 is 0.0501 minus V7. It's equals to 0.08 minus 0.08 minus V8. It's 0.00479, which will give us our effective volume as 0.0453 cubic meters. This is our effective volume. That's what they asked us to calculate in question number 2. And then we go to question number 3, which says calculate the temperature and volume of air delivered per stroke at 1500 kilopascal. 1000 kilopascal, it's here. 1500, the pressure 1500 kilopascal is pressure number 4. So we are asked to calculate for the temperature and the volume delivered. First, let's start with the temperature. Temperature number 4. We can use this line from this point to this point. We have the pressure here, which is P4, P and T4. That's what we're trying to get. We do not have T4. Here, the pressure will be equal to P3, which we have calculated. P3 we've calculated somewhere. P3, yes, this is the value of P3. 3 we've calculated here. And then here, the temperature, we know from this point, this line is the isothermal line. The temperature at this point, it's equals to the temperature at this point, and it's also equals to the temperature at this point also. So let's name this 3 prime. Since 3, it's this point. We're going to use T, it's question number 3. T3 prime divided by T4, it's equals to bracket 3 P3 prime divided by P4, all raised to n minus 1 divided by n. We are trying to get temperature number 4. Then let's do this. T4 divided by T3 prime, it's equals to P4 divided by P3 prime n minus 1 divided by n. So if you're wondering what I did there, is T1 divided by T2, it's equals to let's say P1 divided by P2 is just for example. We do this, and then we know this will change for us to cancel. This will change, this will be on the top and this will be on the bottom. This is exactly what I did here. And then from here we substitute T4, it's equals to T3 prime, which is the temperature that was given as initial temperature, this one, 291 times this P4 divided by P3. P4 divided by P3 can be equals to K, which is our stage ratio. Let's just put K, which is 2.466 raised to N, which is 1.3 minus 1 divided by 1.3. And then our T4, it equals to 358.388 Kelvin. That is pressure. It's temperature number 4. They said we must calculate for the temperature and the volume. For the volume, we are going to use this formula. P1 V1 divided by T1, it's equals to P4 V4 divided by T4. The volumes, we are going to use the effective volume. For P1, which is at the start of the cycle, we are going to use P1 will be V1 minus V8 divided by T1. And then here will be P4 divided by T4. We are going to use, to put the effective, this is the volume of air that is delivered at 1500 kilopascal, and we are going to say V4 minus V5. We are going to treat it as if it is one line from here to here. This is what will guide us to get the correct effective volume, because we know if it was one line, the temperature will be higher than this one. The temperature now at T4 will be lower because of the intercooler. That is what will guide us so that we are able to get the correct effective volume from here to here, from here to here. So Here we are looking for this. We make it the subject of the formula. V4 minus V5. It's equals to P1 times T4 divided by T1 times P4. And then they say times V1 minus V8. Our P1, it's given by 100. Our T4, we just calculated T4. It's this 358.388. Our T1 is 291. Our P4, it's 1500. Our effective volume, this value will be 0.0453, and here we are going to get 0.0071372 cubic meters. And then we go to the last question. They say calculate for the work done, and we are given R as 0.92 kilojoules per kg Kelvin. We are going to use work done, it's equals to X n divided by n minus 1 MRT. Since they gave us n R, we must use the one which has R. P X plus 1 divided by P1 raised to n minus 1 divided by xn minus 1, which would be minus 1, close bracket. And then from there we substitute. Remove these papers. X is 3, n 1.3, 1.3 minus 1. Mass, we are using 1 kg times 0.29 times temperature number 1, it's 291. P4 1500, P1 1000, brackets raised to 1.3 minus 1 divided by 3 times 1.3 minus 1, which will be minus, let me write it like this, it will be minus 1. And then we calculate, and I got that our answer is equals to 354.7 kilojoules per kg. Why per kg? Because we have used 1 kg, and this is our work done. And that's how we go about answering this question. I will see you on the next lesson.